So welcome to the Picture Language Seminar. It's a real pleasure today to have Eric Carlen as our speaker. Eric,
Yes, Arthur.
Student at Princeton, got his PhD in 1984, was then at MIT. Afterwards, spent some time at Princeton, 6 years, and is currently professor at Rutgers. He's well known for proving many different inequalities. And today we'll talk about quantum entropy inequalities. So it's a pleasure to have Eric, and I welcome you, and the floor is now yours.
Okay, let's bring up the right version of this. Okay. Sorry, let me get this. Okay, very good. So, doing just not full screen mode here. Not sure why not? Okay, well, we'll go with this. I hope the slides are readable, it's a little smaller. I'm going to be talking today about an approach to estimating quantitative rates of approach to equilibrium for quantum Markov semigroups. And I'll begin by explaining a little bit about the origin, about how these arise actually in physical systems and what the problem is. And there's going to be a general approach for doing these things that I'll develop. They'll be concentrating on work later on that was done by myself and Jan Maas and some new developments. But the beginning goes back to the 1970s.
Eric, if you can go to full screen, it would probably be a little easier to read.
Okay, let me drop and see if I can go to full screen somehow. Stop share. Let me see. Okay, try again. Okay, and let me adjust this so I can see everything. Good. Okay, hopefully that's a little better. Yes. Okay. Good. Okay, so Brian Dave is considered a physical system and consisting of a closed system coupled to a heat bath. The heat bath consisted of an infinite bath of fermions at an inverse temperature beta. Fermions were used because the annihilation and creation operators are bounded, so it's a little technically simpler, but anyway, we have a full Hamiltonian, which involves the Hamiltonian of the original small system, the heat bath, and the coupling, which has certain reasonable conditions imposed upon it. Now you take a state rho on the small system, you tensor on the equilibrium state as a vector state in the GNS representation to get a density matrix on the full combined Hilbert space, evolve that forward under the interacting Hamiltonian with the lambda in, and run it backwards. So we're looking at the interaction picture, if you like, run it backwards in terms with the interaction turned off. Okay, and then finally, to get back down to the laboratory system, you take a partial trace and project out, and this gives you a rho lambda t. Okay, you rescale time by lambda squared, the square of the coupling constant, because that's what happens when you go through the computations and eliminate to get a close. It's a very simple calculation using Duhamel's formula, and you just eliminate stuff in the right way, and this is what you find. So Davies proved that under reasonable conditions, then as lambda goes to 0, this rho t lambda thing converges to a semigroup. So the memory effects are washed out in time, and you get a semigroup G. And he was able to provide an explicit form for the generator. Okay. Now, when he was doing this in 1974, people were just beginning to recognize the role of completely positive operators in quantum mechanics. He doesn't mention the word in there. He does talk about these things being positivity preserving, but we'll come back to the processes that he had because they satisfy a number of conditions that will be important to what's going on. Okay, so the operations that come out of Davies' analysis are specific examples of quantum operations that we'd like to discuss now a little more generally. So we're going to be discussing things in a finite dimensional case because it's technically simple, and ideas that are understood here can be easily translated by people who know the Tomita-Takasaki theory and whatever. For von Neumann algebras, that's necessary. The gist of the matter is here. So let's let phi be a linear map from the m by n matrices to n by n, and we equip the n by n matrices with the Hilbert-Schmidt inner product, making it a Hilbert space, and we always use a dagger to denote the adjoint with respect to the Hilbert-Schmidt inner product. Okay, so a map is unital if it takes the identity to the identity, and it's trace preserving if the trace is the same before and after applying the map. And it's easy to see that phi is unital if and only if phi dagger is trace preserving. Okay, now here comes the notion of complete positivity. A map phi is positive if it takes positive matrices to positive. It's too positive if this block matrix, if you apply things to a block matrix, if the block matrix is positive, you apply phi to each of the entries, and that's still positive. That's too positive. Classic example of a transformation phi that's positive but not too positive is the transpose. Okay, so this is a more restrictive condition. Complete positivity means that you're positive for all k positivity being defined in the obvious way. Okay, and now here's an example. Consider the map phi, which just conjugates x by v, sending it to v star xv for some v. And now if you write out the block form of that, you can see that this block form is just given by conjugation by the diagonal matrix left and right. So it's certainly going to be positive. And so any linear combination of such things is going to be a completely positive map. Okay, this looks like the simplest possible example, but in fact, it's pretty much all there is. Okay, so if phi is completely positive and unital, its adjoint is a completely positive trace preserving map. And so evidently it takes density matrices to density matrices. And such maps are known as quantum operations. Okay, and here's an important example that will come up. Let m and n be natural numbers, and we can think of matrices in m sub m times n as m by m block matrices with entries in mn. And this map xc sub m just takes the m by n matrix and it sticks it in on the diagonal going down a block. So this is completely positive. In fact, it's a star homeomorphism into the larger matrix algebra. Okay, the dual of that turns out to be just the partial trace. Okay, so these are two quite important examples of completely positive maps. And so the partial trace is a quantum operation, and its dual is this gadget up above. Okay. Now, there's a Stein spring factorization, and in this simple matrix setting that we're talking about, it's given as given by the following, and you'll recognize this as having shown up on the first slides in the discussion of Davies' work. You take some A, which consider it as a state, I could call it rho, on your laboratory system. You tensor onto it the vacuum vector, this 1, 1, which means you're really sticking it up in the upper left-hand corner of a block matrix. Okay. Now you apply some unitary on the block matrix, which is a global evolution of the system and the environment together. Okay, this gives you a new density matrix on the universe, as it were. And then you finally do this partial trace operation to get back down to what's on the laboratory. And that's what these things all look like. And now if you just take this general form, I mean, this is, you get the so-called Krauss representation, and you see that these V's, if you write out what this is, taking the partial trace, the V's are the blocks of U which come from the first column. That's all they are. So in fact, this simple example we had was everything there is. So this is where the Krauss representation comes from the Stein-Spring representation. Okay, so we're going to be considering here quantum Markov semigroups, which are nothing other than semigroups that are completely positive unital maps. These things, and the adjoint of these things, well, if these are unital, then the adjoint of these things is trace preserving. So it's traditional to put the PT dagger on the quantum operation part, the part that's trace preserving. So this is the Schrodinger picture, if you like. The PT is a Heisenberg picture, just nomenclature. That doesn't, if that doesn't help, don't worry about it. But the PT rho is the thing with the dagger on it that's going to update density matrices, and these are called quantum dynamical semigroups. Okay. Now, since a quantum Markov semigroup is unital, the number 1 is an eigenvalue for each PT, and by a simple Frobenius argument, there will be invariant density matrices sigma for the dynamical semigroup, and we'll generally be interested in the ergodic case where there's exactly one such invariant state, as in the case treated by Davies, where it turns out to be a Gibbs state for the system Hamiltonian with the inverse temperature determined by the heat bath. If things aren't ergodic, you can decompose them to ergodic pieces. Okay, so in this finite dimensional setting with a unique invariant state, very soft compactness arguments provide a spectral gap from which it follows that for any starting point rho in your state space, that's this factor S, the evolution under the quantum dynamical semigroup will take you to the invariant state sigma with exponentially fast convergence in the Hilbert-Schmidt norm. Okay. Now, we would like to quantify the exponential rate as precisely as possible and in the more meaningful trace norm. Of course, in a finite dimensional setting, all of these norms are equivalent, but of course, going back and forth between them, there are factors which depend on the dimension. And in the problems that are physically interesting here, the state space is going to be a space modeling a large number of particles, and the state space will have a dimension that's independent, that is exponential in the number of particles. And so we don't want to make advantage, we cannot use and get meaningful results by passing back and forth between Hilbert-Schmidt norm and Weichmann norm with constants that depend on the dimension. Okay, so to get to the trace norm, it's natural to look at the quantum relative entropy. This comes in. So the quantum relative entropy is this quantity defined on the first displayed equation. This is commonly called the Umegaki relative entropy. Log of rho minus log of sigma is one way you could interpret the classical quantity log of rho divided by sigma. There are others, and there are other versions of relative entropy, but this one does have a direct physical meaning. Loosely speaking, the number of experiments required to distinguish a state rho from sigma with an error probability of size epsilon is minus log epsilon divided by the relative entropy. So this is in complete analogy with hypothesis testing in classical statistics. So it's a physically meaningful quantity, and it does measure, therefore, a good measure of the divergence of rho from sigma. And while it's not a metric, it does dominate this L1 metric, which is what we're interested in. This is the so-called Pinsker inequality, and this follows directly from the classical one via the data processing inequality, to which we will come next. But right, so notice that if you show that the relative entropy is decreasing exponentially fast, you show that rho is converging to sigma exponentially fast in the norm of question of interest. Okay, now running through this investigation, there are going to be two key inequalities. And the two inequalities that are the star of this talk come from a 1973 paper of Elliott Lieb on the Wigner-Yanesy-Dyson conjecture. The first one of these is the so-called Lieb concavity theorem. And here it is stated, it's a joint concavity theorem. So if you put a minus sign in, it becomes convex. And so the parameter here is the t, which goes between 0 and 1. If the t is 1/2, this is a theorem proved by Wigner and Yanesy. And the conjecture, which seems to have been made by Dyson, is that one should prove it for other values of t. And okay, this was one of the things that was accomplished in Elliott Lieb's 1973 paper. The theorem down below doesn't have a name. This is from the third theorem of this same paper. Elliott showed that there are 5 theorems in this paper, and Elliott showed that they're all equivalent to one another. And he derived the one he worked hard to prove was the Lieb concavity theorem, and the others then follow by shorter arguments. This theorem was overlooked. I'll bring that out a bit in the title, so it didn't get a name, but it's the other key to making things work in our program. Okay, and both of these are entropy inequalities and might be a little hidden right now, but let's explain why that is. Okay, so the Lieb concavity theorem has an immediate consequence. In 1975, Goran Lindblad proved, using the Lieb concavity theorem, what is now known as the data processing inequality, which is here in the middle of the page. And this says that if you take any two states, rho and sigma, any two density matrices, and apply any quantum operation to them, you decrease the relative entropy. So roughly speaking, what this says is that applying a quantum operation can only make these two states harder to distinguish. Okay? So this inequality has become one of the cornerstones of quantum information theory. An interplay between convexity and monotonicity is going to be important in the applications that follow. So let me spend a little bit of time, this may be familiar to a number of people, explaining how you get back and forth from the LCT, which is a prototypical convexity theorem, and the data processing inequality, which is a prototypical monotonicity theorem. Okay? So to go from LCT to DPI, you take the special case k equals 1, just take the identity operator, and so the k's are gone. And then what this theorem asserts is the convexity of this thing that's displayed in the middle of the page. And if you just take t going to 0, compute the derivative, exactly what you get is then, in the limit, the joint convexity of the relative entropy, because the Lieb concavity theorem says that before you take the limit, this thing is jointly convex in x and y. So that's the joint convexity. And then from there, what does one do? Well, you use this Stein-Spring factorization that we recalled earlier. And the key thing here is that this partial trace operation can be written as an average over unitary conjugations. Since it's an average, this allows one to exploit the convexity to get an inequality. And this is where the whole inequality comes in. The other three factors in this factorization don't do anything. I mean, the relative entropy is unitarily invariant, so the unitary in the middle does nothing. And this initial psi sub m just pads things with zeros, so that does nothing. And so all the action is in this final partial trace, but since it can be written as an averaging operation, the convexity coming from the Lieb concavity theorem gives you the monotonicity that is the data processing inequality. Okay? Now, in exactly the same way, one can prove a monotonicity version of the other theorem, the other convexity theorem that I wrote down for you. And in fact, one can prove monotonicity versions of all of the convexity and concavity theorems in Lieb's 1973 paper. And for some reason, this was not done, and people had to start over from scratch a while later, but we will also need the convexity version of that. So here are the convexity versions of these two theorems of Lieb. The first one to come about was done by Ullmann, Armin Ullmann, in 1977. And this is what it ends up looking like. Okay. If you take the map phi dagger to be the partial trace, it's easy to see that this reduces directly to the convexity theorem. So the passage back from this to the convexity theorem is a simple matter of taking phi dagger to be the partial trace. Same thing with the one down below. Take phi dagger to be the partial trace, you recover the convexity. Okay. Now you can get these from the convexity theorems by the same argument that Lindblad used, but that's not how things were done. Things were done by a rather different argument. And indeed, Ullmann proves a little bit more, because Ullmann proved that this, in the theorem on the top, you did not need phi dagger to be a quantum operation. The phi didn't even need to be too positive. It just needed to satisfy a so-called Schwarz inequality. Likewise, when Petz proved the theorem down below, he required phi dagger to be too positive. Turns out all you need is the Schwarz inequality. And so a lot of recent work has been devoted to understanding these monotonicity versions, and an advantage of them is they hold for a wider class of maps and determining what that wider class of maps is. Okay, and this is the Schwarz inequality I was talking about. And I won't go into that today because I will be focusing on quantum operations, but if you want to look up my 2022 papers, also with Müller Hermes and Haonan Zhang on the archive, then you can find much more about these extended versions of these inequalities for larger classes, for optimal classes of maps that go beyond complete positivity. Okay, but let's go back to what we're talking about. So let's bring some of the ideas together. We consider a quantum dynamical semigroup now with an invariant state sigma. And then by the invariance of sigma and the data processing inequality for any density matrix rho, okay, let's look at the relative entropy of the time evolution at time t of rho with respect to sigma. Okay, now I can stick the PT dagger on sigma for free because it's invariant. And then the inequality that's at the right-hand side over here is nothing other than the data processing inequality. So what this says is that in complete generality, this function, which takes t to the relative entropy of the evolution of rho at time t with respect to sigma, is monotone decreasing. Okay. Now, the research in the rest of this lecture is devoted to the following questions. I'm trying to get this yeah, good. Under what circumstances can we write the rho, this evolution, this semigroup, as gradient flow for the relative entropy on this space of all density matrices? Now recall what the gradient flow equation is and why we want to do this. The gradient flow equation in Rn for a smooth function f is x dot equals minus gradient f of xt. Okay. Now then by the chain rule, if I compute the time derivative of f along this flow, I get gradient of f dot x dot, which is minus gradient of f squared. And so it's monotone decreasing. Indeed, another word for this gradient flow is just steepest descent. So when you have something that's decreasing like this, you might hope it's steepest descent. And the advantage of doing that is that when it's steepest descent, there are techniques for quantifying the rate of convergence if one can quantify, say, if the f turns out to be convex and how convex that is. Okay, so the second question is when it is possible to write this evolution equation, this gradient flow for the relative entropy with respect to some metric, under what circumstances can we find such a metric and relate the rate to geometric properties of this metric? Is the rate of convergence exponential? Okay, and of course, there are going to be positive answers to these questions, or I wouldn't be talking about this. Let's briefly clarify this thing just to make sure everything's clear about what gradient flow is and why it is desirable to put things in gradient flow terms. Okay, so here's the gradient flow equation. And let's suppose f is twice differential and its Hessian, that's the d2f, is such that it's bigger than twice lambda times the identity, that take lambda to be positive. Okay. Now, if we look at this d by dt of the square of the gradient of f along the flow, you get the Hessian in the middle, but by the hypothesis that's up above, you get that this quantity is decreasing at rate minus 2 lambda. So this gadget, this gradient squared, is decreasing to 0 exponentially fast. But remember what this was. This gradient squared is just the rate of decrease of f. So integrating things up, one gets that this f is less than is less than the initial rate of decrease of the functional f. And so this is a sort of generalized logarithmic Sobolev inequality. The f on the left is the entropy. The gradient of f squared is the entropy production. And this shows, again, by Grunwald's inequality, that the entropy decays to zero exponentially fast. Okay, so this is something that's been exploited extensively in PDEs and studying the rate of convergence in PDEs. And Felix Otto has been one of the great drivers of doing this method and introducing metrics based on mass transportation constructions for which one can find this convexity. See, there are many ways one can write an equation as gradient flow, and for different metrics and different objective functionals. And the trick is to find one so that you get this good convexity property. Okay, now that's what we'd like to do here. So if we can write our equation as gradient flow, and if we can show that the relative entropy function is convex, uniformly convex in this sense, then we will get a rate of convergence to equilibrium. Okay, now it turns out that a quantum Markov semigroup does not always satisfy gradient flow for the relative entropy. There's a necessary condition, and this was proved by myself and Jan Maas in a 2020 paper. There's a certain inner product on the there's a certain inner product on the space of density matrices, which comes up in mathematical physics. It has a name. It's the Bogoliubov-Kubo-Mori inner product, and the generator has to be self-adjoint with respect to this inner product, or it's just cannot possibly be written as gradient flow for any metric. So what are these various things? They come up. So when you write down an inner product between two matrices, say B star and B and A, and you weight it with respect to sigma, in the non-commutative setting, there's a question of where you put the sigma. So you can put it on the right, you can put it on the left. And as you see here, you can put some of it on the right of A and some of it on the left of A. However you do that, you get something that gives you a positive quadratic form. So this gives you an inner product. You can integrate over these things. And so this gives you a whole family of various inner products, okay? Conditioned by, indexed by measures on 0, 1. So the Gelfand-Nymark-Siegel inner product, this is the first one that came up. This corresponds to taking the delta mass 0. And that just means that you put the sigma all the way on the right. Okay, so the simplest thing, the sigma goes on the right, that's what it is. Another one that has a name is the Kubo-Martin-Schwinger, and this is the much more symmetrical one where you put the sigma half and half. And then the BKM is the one that you get when you integrate over this, so this is also sort of symmetrical. Okay, now these symmetrical things, being self-adjoint with respect to something that's symmetrical like this, you can work out conditions for it, but being self-adjoint with respect to the GNS inner structure, which is not symmetric, which has all the sigma way off to the right, turns out to be a very restrictive condition. And it turns out that if something is self-adjoint with respect to the GNS inner product, it's self-adjoint with respect to all of these others, including the BKM. So within the class of things that are of operators that are symmetric with respect to this Bogoliubov-Kubo-Mori inner product, there's a subclass that's inner self-adjoint with respect to the GNS inner product. And with this restrictive condition, we have a good structure theorem for what the generators of these things look like, and we can carry everything out. Okay, so we can't do it in general, but one can do it for this. And by the way, the semigroups that were constructed physically by Davy's argument do have this property of being symmetric with respect to the GKS inner product. Okay, so here's some structure theorem we'll use. In 1976, and this goes back quite a ways, let's consider a semigroup of quantum operations that satisfies the detailed balance condition, meaning that each of these PTs, and therefore the generator L, is self-adjoint with respect to the GNS inner product. Okay, then the generator L and its adjoint have the following form. So you have this form here. Now, notice that if the V happened to be self-adjoint, so Vj star was equal to V, you could write this as a double commutator, and it starts looking a lot like a Laplacian, right? Because a single commutator is a derivative, so this is some sort of Laplacian operation. Okay? Now, the important thing that really makes this work is that these V's are not just any old V's, but these V's happen to be eigenvectors of the modular operator. This operator where you multiply on the left by sigma and divide on the right by sigma is the so-called modular operator of Tomita-Takasaki theory. Okay, one doesn't need to know that to appreciate it, but it's a fairly simple operator to diagonalize. And the thing which makes things so simple is that its self-adjointness with respect to the GNS inner product forces the operator to commute with the modular operator, which means you can simultaneously diagonalize them. And that's what gives you a big leg up and gives you this structure theorem for these things. Okay, so now we would like to introduce gradient flow on this space. Okay, so we're going to identify the tangent space to the space of all density matrices as the point rho in terms of the self-adjoint matrices that have trace 0. Right? Because I can take rho and I can add rho plus epsilon A to it, and I've still got a density matrix. The cotangent space can also be identified with script V through the same dual pairing. Now, if we've got a smooth Riemannian metric on G, so that's an inner product here over here, this quadratic form, that introduces a map from the tangent space to the cotangent space as follows, just in terms of the quadratic form in the usual way. And then there's the inverse guy, the G inverse, which takes you from the cotangent space to the tangent space. This is what we're most interested in working with when we're talking about gradient flow, because when you're doing gradient flow, what do? You have a function f, and its differential, which is an element of the cotangent space, that's defined without respect to any inner product. It's just this thing right here, and unfortunately this thing is on top of it, but you just take a derivative in the usual way. So the cotangent, the cotangent vector associated to f, that doesn't depend on the metric. But to get a tangent vector out of it, we need to map it into the tangent space, so we get the gradient flow equation, and that's where the metric comes in. Okay, so the gradient of a function on our density matrix space is you take the differential, and then you apply this matrix to it. Okay. Now the differential of the relative entropy is just log rho minus log sigma. You apply this matrix to it, and so what we are looking for is this metric that is going to convert log rho minus log sigma into our generator. So can we find the metric so that this always happens? And in the case we can. Okay. So there's a classical model for this. Again, Jordan, Kinderlehrer, and Otto's name is covered up there, investigated simple PDE version of this. So now rho is not a density matrix on the slide, it's a probability density RD. And we can look at this Kolmogorov backward equation for rho that comes up here. And this also describes, as Jordan, Kinderlehrer, and Otto showed, gradient flow for the relative entropy with respect to the classical relative entropy, written here as an integral, that's the only difference, with respect to the 2 Wasserstein metric. And the K rho operator, in that case, it's given right here. It's just the divergence of multiply by rho times the gradient of psi. And the reason you get a linear equation out of all this, because you're going to be applying this K operator to log rho. Okay, but if you do grad log rho and multiply by rho, that's gradient rho, and you take divergence and you get the Laplacian. So the key formula, which makes everything work and that gives you a linear evolution equation out of this gradient flow of a non-quadratic function, is exactly this identity here, and one needs a quantum analog of that to make things work for us. Okay, and there is one. So to move in that direction, we'd like to introduce our derivatives, the gradient. We want the formula of this grad log rho formula for ourselves. So we take a generator. It's specified by these functions v, and the sigma, and we'll introduce the notation partial sub j a is the commutator of v with j. Recall that commutators are a derivation like derivatives, so this is not so bad. Okay, define a Hilbert space Hj. J is the index set over the V's that show up in our decomposition to be the direct sum of a bunch of copies of these A's. Okay, and if we've got a vector in here, let Aj be its component. Okay, so we pick some ordering and we write the vectors like this, and we equip this with the usual inner product. Okay, so this will give us now a gradient and a divergence operation. So given a operator A, so it's gradient, there should be an A is missing here. So you take the first derivative of A on out to the last derivative of A. So that's just the usual thing. And the derivatives here are commutators. The divergence of something is exactly the same with its minus sign stuck in. So you take the commutators and sum them up. So this gives you a non-commutative gradient and non-commutative divergence. Okay. Now the last thing one needs is the appropriate multiplication for rho. What does it mean to multiply by rho? And again, in the non-commutative setting, there are lots of ways you could do it. And the way that's going to make everything land on its feet is as follows. Okay, for the j's to v, we're going to have to do this in a way which depends on the j's. This takes into account these are the eigenvalues, differences of eigenvalues of the density matrix, the invariant density matrix. So that comes into play. And so what you do is you take this weighted version of rho and this otherwise weighted version of rho, and you integrate up in S, just as you would in the Duhamel type formula, and this multiplies by rho. So notice if the rho and the A commute and the WJs are 0, then this really just is multiplication by rho. Okay, and the inverse of this is given by that. This just comes from the simple relation between the derivative of the exponential and the derivative of the logarithm. And finally, m rho of A means you do the right version of m in each one of these coordinates. And then there's a chain rule for the logarithm. So this is sort of the key theorem, the key lemma in what Jan and I proved. It's probably easiest to understand if you look at the case where the sigma is a multiple of the identity, in which case all of the omega j's are 0. Then this thing that's on the left just becomes another commutator of rho, or rather a derivative of rho. And now it really just says something like the derivative of rho is equal to rho times the derivative of log rho. Okay, that was the formula which gave you the linear equation. And then you define K to be this. This gives us our metric. And it's simple calculations from this point built on this model. We have this identity. So our generator can be written in this form, and it is gradient flow with respect to the Riemannian metric introduced by this. Okay, now this was also done in 2017 by Milke and Mittensberg. They constructed a metric by different means for, again, getting this thing, sort of the master equation, again, under detailed balance condition is gradient flow for the relative entropy. The metric is not unique. Their metric was different from ours. And in a 2020 paper, Jan and I gave a more flexible construction yielding a very wide range of all of these metrics. Okay, so now that we've got this metric, what do we want to do with it? Well, we wanted to study the rate of approach to equilibrium, and let's see how we're going to do that. So here's where the mass transportation comes in. We want to write our metric in a Grenier-Benamou formula. And so this is, okay, for people with a fluid mechanics background, we're going to an Eulerian framework, the usual discussion of mass transportation. The original discussion a la Monge-Kantorovich is more Lagrangian, keeping track of how particles move. We'd like to keep track of how densities move instead, because, well, you can't keep track of how particles move in the quantum setting anyway. So here's a formula for the two Wasserstein distance between two densities, rho naught and rho 1 on Rn. And you connect them up with all paths, and then you take an infimum. So this says that the paths satisfy the continuity equation for a gradient vector field. This is the action that you minimize. This is the metric, the speed. And it can also be written in this form. Notice the rho is upstairs here and it's downstairs here. So you can use not the velocity, that's this, but rho times the velocity is the momentum. So this momentum over rho has good joint convexity properties, and that makes this second formulation much more useful, and it will be key to what we do here. Okay, so now we do the same thing in our case. We take this G rho rho, this is what the inner product is. It's defined by this in terms of the K inverse, and we multiply and divide to make it symmetric, to put a K rho in there. And okay, so we can write, yeah. So if you write this as the K times the B, this is the gradient, then this inner product just can be written like that. And here's what we have. So the distance between two, now these are back again density matrices, it's the distance between these things. This is the continuity equation up here, and this is the condition on the endpoints. Now we want to make a change of variables to bring this into the other Renan-Hubenier form, which allows us to take better use of the convexity. And so introduce A of t equals this m times the gradient, and recall that the K has gradients built into it. And so using a simple minimizing property of gradients, what this reduces to is this form over here. So now the m, we're dividing by m because we multiplied by m up here. And so this gives us this form. This is the analog of the Brenier-Benamou formula. Okay, so let's recall what this thing is. So this AM, it's equal sum over these J's of all of these things. Now, hopefully, you can still recall back on an early slide, I quoted the second theorem, a second theorem of Elliott-Lieb, and a theorem of Elliott-Lieb said that these traces of quantities like this were jointly convex in everything in sight. That's the A's and these operators, which are down here. They happen to be very closely related in this case, but in the end, this could be any positive X, this could be any positive Y, and these were called K's before. So there's some joint convexity in there. Because of the joint convexity, then the same sort of argument using the same argument that Lindblad used to prove the data processing inequality gives you the monotonicity version. That shows that this inner product, which is here, is actually a monotone metric. And the connection between Lieb's theorem and monotonicity to this was not realized for a long, long time, certainly not in the original work of Petz, but anyway, from our point of view, I mean, that's what it is. So it's Lieb's theorem says that this thing is monotone. Now, that's going to be the key to getting the entropy inequalities out, as I would like to explain coming up here in the last few minutes. Okay, so here's the thing. We want to get our hands on geodesic convexity. And so now we're back in a finite dimensional Riemannian manifold. That's what we've got. If we have density matrices on a finite dimensional Hilbert space, then this space script factor S is a finite dimensional manifold. We've got a metric on it, smooth, so it's a Riemannian manifold. Okay. The distance between 2 points is given by taking the infimum over the action, connecting them up, and now let's consider a function f on this manifold and let grad g denote its Riemannian gradient. Okay, a function is convex if whenever you take two derivatives along a geodesic, okay, it's lambda convex if the second derivative is bigger than lambda times the speed along the geodesic. Okay. Now it's a standard result, just as we discussed earlier. Let's go quickly. It's a standard result that if this f happens to be lambda convex, then the flow pushes things together at an exponential rate, and you converge to equilibrium at an exponential rate, and so forth. Okay. Now, if you want to take this approach directly, we would have to find out what the geodesics are for the metric we've constructed and take two derivatives along them. And this is a mess, and we've never gotten anywhere doing that even for simple cases. But there's a very good way to do this to avoid dealing directly with convexity and to use monotonicity instead. And I'll explain how this works. This is built based on work by Daniere and Savaret and some interesting just plain differential geometry. If you take the action, so take your curve and get a 2-parameter family of curves by applying the gradient flow operation to it at time t. Okay, so there's the original curve with, say, a geodesic, and you flow it along. Now, you can look at the action along this one parameter family of curves, and you can ask, is it decreasing relative to the initial action? And if it is decreasing at this exponential rate, then F is geodesically lambda convex, and one has everything that one wants. Okay? So now we're in much better shape because with this result of Danieri and Savary, we don't have to find the geodesics, and we don't have to compute two derivatives along a geodesic. We just need to differentiate the action. And it turns out we don't even need to do that, okay? Because this quantity that we've got to differentiate is closely related to the monotone metric that was discussed earlier, that provides the convexity theorem of Lieb. So using this, one can prove the required monotonicity inequality in a number of important cases where we don't have to take any derivatives at all. We throw everything back onto the monotonicity version of Lieb's theorem. I'm going to flash some slides up quickly to get to the end so that I finish on time, which I've got to do, just 3 slides. There's some stuff with intertwining operators that comes up. If people are familiar with the Bakri-Emery approach in the Bakri-Emery approach for proving logarithmic Sobolev inequalities, you commute a gradient past the Laplacian and a Ricci curvature term shows up. So there's an intertwining relation by moving gradients past the generator of our map. And if you get the right sort of thing, intertwining relation, moving things past, okay, and then you use, here's the bottom line, right from here to here. This inequality, we've already brought out a -2 lambda from the intertwining, and this inequality is exactly Lieb's monotonicity theorem. This gives us the inequality we need from Danieri and Savary, and so this then proves that things are decaying exponentially fast. Using exactly this technique, Jan and I proved sharp entropy dissipation inequalities for boson and fermion Ornstein-Uhlenbeck operator semigroups. And currently, Michael Loss and I are working on proving or proving, actually in the midst of it, such entropy productions for analogs of a quantum Boltzmann equation, and have succeeded in a number of interesting cases, but much remains to be done. And I thank you for your interest. Okay, so that's it.
Well, thank you very much for a beautiful talk. You covered a lot of ground, and I'm sure that we're going to have a lot of discussion and questions. So maybe for the time being, I'll stop your sharing and ask for people who want to make comments or questions to turn on their videos so we can have back and forth.
Professor, can I ask a question?
Yes,
Okay.
So you define the Washington distance of order 2. So do you have some kind of like terrible inequality? So there's a boundary between the Washington distance of order 2 and the record.
Yes, right. So there are a number of other applications, and so Jan and I proved a Talleyrand inequality in the 2020 paper. So I focused here. There's a lot in this talk already to keep this focused on just one question: how fast do systems approach equilibrium in a quantitative way? But the analogy with the 2 Wasserstein metric is really close. So the hint at it I've given in this talk is I've showed you how Grenier-Benamou formula, close analog of a Grenier-Benamou formula, comes into play, and you can write the metric like that. That's, I guess, can give one confidence that there really is a close connection with something like optimal mass transport, and then one can use adapt proofs from the classical theory to the quantum setting.
But do you have any like special comment on the states, like require them to be at least one of them to be separable? As a product. Because in the original line question, it about one of the states or one of the distribution would be the product. But do you still have such requirements?
So I guess we have some Talleyrand with respect to the invariant measure, which is whatever it is, but not sure it's not a separability condition per se in this case.
Is the Wasserstein distance about 2 defined?
Well, there's also a Wasserstein distance of order 1 that you extract from this. So I mean, because we have from the differential structure given in terms of these commutators, so the Wasserstein 1 is the Cantor-Rubinstein metric. So there's a notion of distance that comes from having a bound on the commutators. And so if you take that, then there's a natural version of a Wasserstein 1 metric. And some of the analogs of Talagram type inequalities fit better with the Cantor-Rubinstein metric. And so we do that in this paper also. So in the 2020 paper, there's a wide range of such things. And other people, I mean, Marius Junga and his group, and people I also did, Dario Trevisan in Italy. So a number of people have been investigating various quantum versions of Talagram type methods and getting them by other means and so forth, and for other specific applications. So it's not just from our work, but one thing we do emphasize in the 2020 paper is that there really is a close connection with the 2 Wasserstein metric and even the 1 Wasserstein metric, and the connection is substantial and close enough that you can prove analogs of a lot of the things you would expect.
So maybe we could ask for other questions and continue the discussion with.
Yeah, can I ask? Sorry.
Marius, yes.
Very short. Do you want to say something about how intrinsic the choice of your AJs are? I mean, is everything you're describing intrinsic?
The A.
Well, I mean, when you derive your derivatives, it looks like you make choices about these VJs.
Well, the VJs are pretty much, I mean, the VJs have to be eigenvectors of the modular operator. And so insofar as your sigma has really disjoint, I mean, it has non-degenerate spectrum. And even if the omega, then if you go to the extreme case where the Bohr frequencies are all disjoint, then you pretty much just got one choice for what these VJs can possibly be.
Yeah, I'm just probably thinking more about infinite dimension, where sometimes these VJs might not really exist, right? So you have to write it all in terms of the generator itself.
So maybe
Right.
it all could go back to the modular operator, and you could have
the gradient form. Yeah, I think that's what's happening, right? I mean, that intrinsically you can talk about the derivative from the gradient form. Right. Anyway, I think it is intrinsic even in infinite dimension. It just gets trickier to write.
I would think that's most likely the case. The main questions that are difficult to handle. These things have been being looked into in particular by Melchior Wirth, and he has done a very nice extension of this theorem of Aleki to the general infinite dimensional von Neumann algebra case. And so a good bit of it goes through, and there are some points where you get some tricky domain questions, but
yeah, sure.
I think I think his beautiful work is another example of this case, that once you understand everything that's going on in the finite dimensional case, that you can
push it
you're
through.
not far off from this, right? So, but to the thing that, and again, these guys deserve mention. I guess Melchior Wirth and Haonan Zhang are 2 postdocs of Jan Maas now at IST in Austria. And another thing they've done, I flashed up briefly on the slides here at the end, these intertwining relations that we used, which were to move some derivatives past and get us in a position so that we could use Lieb's monotonicity theorem to apply the Daniel-Savary thing. And there we had a lot of monotonicity, because if you notice, there's a semigroup PT dagger that's applied always to a gradient. And it turns out they observed that you can modify this thing because you can assign it to be something else on the orthogonal complement to the gradients. And then in the dual form, you get a lot more out of this. So this intertwining relation that Jan and I exploited in a simple way does have a lot of arbitrariness in it. This arbitrariness has been realized by Haonan Zhang and Melchior Wirth, and it is now being used to give more as a much more powerful tool. So it's, for instance, if you apply it in the naive way that we did to the complete depolarizing channel, you don't get anything, right? But if you apply it the way they do to the complete depolarizing channel, you get even the right thing for the 2-bit case and something good in general. So yeah, there's a lot of arbitrariness in here, and we're trying to understand what that is. And this arbitrariness is a good thing, because if you've got choices and can fiddle around with them, you can get more done. And these guys have given a great example of how that works.
I think we agree that these intertwining relations are a little bit too strong, right? In a way, but it's now replaced by Ricci curvature in many cases, right? So
right. I mean, it is sort of the analog. I mean, exactly at the corresponding crucial step in the Bakri-Emery work, you're commuting the gradient with the parallel Laplacian. So, right, so you first apply the Laplacian and take the gradient, but if you take the gradient first, then you need the parallel Laplacian, and then the Ricci curvature comes up, and it's that Ricci curvature term which makes everything work in the Bakri-Emery method. That's really very close to what's going on in the intertwining here, as far as I can see.
Jordan, did you have a question?
Yes, I did have a question. Yes, so thanks for a great talk. So if I thought about the Monge formulation of optimal transport, just in the ordinary classical sense, I can think about optimizing over a family of transport functions. What is the analog of the family of transport functions which you're optimizing over? If I did a Monge formulation of the quantum optimal transport that you're, the version of the Wasserstein 2 distance that you're discussing, how do I think about it in that way?
Okay, well, this is a tricky question, and there are people who've been trying to work with to work with that. I mean, the problem is, in the classical space, you've got a probability density, and then there are all possible outcomes of any experiment, or just points in the space, and you move the points. Right. And in the quantum system, there isn't any underlying space, because you've got a state, which is a density matrix, but maybe you try to measure momentum, maybe you try to measure position. I mean, all kinds. So there aren't any underlying points, and so this is what makes it difficult to formulate directly a Lagrangian type, as in the original Lagrange Cantorevich, where you're moving the particles along to have a Lagrangian formulation. And this is what makes it so attractive to go instead to the Eulerian formulation of Grenier and Benamou, where you're just working with the densities, but not working directly with a flow. You don't have paths. You don't have paths in quantum. So, right. I mean, you can't track particle motion in quantum mechanics. I mean, in orthodox quantum mechanics, there are not paths of particles going from here to there, and choosing the best path. Well, if there isn't even any path, is kind of hard to make sense of. So, that said, there are people like, again, Dario Trevisan, Francois Goltz, and so forth, other people, and they have been doing things based on looking at Wigner functions and doing optimal mass transport after you've gone to phase space and looking at those densities. And what they get is not exactly the Wasserstein distance. I mean, the distance between something in itself is non-zero and so forth. So it's not a complete analog, but it's basically this whole issue is, you don't have, in quantum mechanics, you don't have paths of particles to look at. And it's like when we talk about detailed balance, also there's this detailed balance condition that came up. In classical statistical mechanics, you've got particles moving around. And what does detailed balance mean? It means if you look at a movie of the particles, you can't tell whether it's running forwards or backwards. Fortunately, you can express that analytically as a self-adjointness condition. That survives in quantum mechanics. But with the movie, it doesn't make sense because there aren't paths of particles to watch.
Well,
so,
oh, sorry. I guess one confusion is I might have naively thought that the transport functions would be a certain class of quantum channels, that you would have a cos function which takes in a state and takes in some channel applied to the state, and then the question is, what is the family of channels that you're supposed to optimize over? But I guess you're saying that it's not quite so simple to characterize in that way, such that you end up getting a distance which is positive semi-definite, that or that satisfies the usual axioms of a distance.
Mm-hmm.
Okay.
Yeah, I mean, that would be, okay, so yeah, so one could, Right. So you could look at a channel that would look at a class of channels that would take rho to sigma and associate a cost to using the channel, and then take the infimum over all that, and presumably that might give you an interesting distance. And
Okay.
I haven't run across anything quite like that being used, and I'm not sure how close it would come to what has been done in. Yeah, that's an interesting idea. That might lead to something quite interesting, but it looks a little. So the advantage of going to this Eulerian scheme, a la Grenier and Benamou, is then you avoid this problem of not having quantum trajectories, and you just have a trajectory in the space of density matrices, which makes perfectly good sense. And then you have a structure which is very close to the classical theory, done from that point of view. And so then you have a lot of classical models for what you might try to do next to prove some inequalities, and they seem to be exploitable. So, but yeah, what you're suggesting sounds very natural and interesting, and so probably should be looked into.
Thank you.
Thanks. Are there other questions or comments?
Yeah, I have two questions.
Michael, yes.
Yeah. Okay. First of all, thanks, Eric, for excellent. You can hear me?
Yes.
Sure. Here, just fine, Michael.
Thanks a lot for a very interesting talk. So I have two questions. First question: which results go over to infinite dimensional case?
Okay. Well, one that was actually cited there is an infinite dimensional case result. So this was this sharp rate of hypercontractivity for the Bose-Mailer semigroup at inverse temperature beta. And so the good thing is that when the bottom line, I mean, this structure tells you what you should try to investigate, and then the tools that one is using in this, at the end, you look at this action functional and you need to know it's decreasing in a certain way. And, we apply this Elliott's second theorem, which gives you this monotonicity of this metric. That's sort of the key step in controlling the monotonicity of action. And so this goes through in finite dimension just fine.
Okay. And now the second question is going back to your very first slide. When you start with the quantum system coupled to the reservoir, to the environment, and then you, of course, grinding out of the environment, reservoir, right? And you arrive to this Markov evolution. Now, for a regional system, you can prove convergence to equilibrium under certain conditions. So you couple either to bosonic or to fermionic reservoir, and you can prove convergence. You can prove return to equilibrium and convergence to equilibrium, right? So, so what I would like to understand, what's the kind of relations, or what's the advantage of one approach versus the other approach?
Well, I mean, the proof of approach to return to equilibrium one finds in Davies' 1974 paper already, but but this is done only by very soft methods. If you want to know what the exponential rate is and how it depends on the size of the laboratory system, then you need to do some more complicated calculations. So this approach, what we're talking about here is how can you get a quantitative estimate on that doesn't depend on the dimension of the system in a bad way. So in particular, in the systems that Michael Loss and I are investigating now, we have n particles with d levels, and they're interacting in pairwise interactions. And we would like to get, and we are getting, rates of approach to equilibrium relaxation that don't depend on the number n of particles, because we'd like to have something that survives and the n goes to infinity limit. So this is what, right? So we'd like to understand this. Just knowing that you approach equilibrium eventually is not enough for many applications because you'd like to know that you have a rate of approach which is independent of the size of the system. And that's what these methods deliver.
But in a regional system, if you take a particle system coupled to the reservoir, right, you don't have exponential approach as a rule, as in general. It doesn't approach exponentially. You don't have a gap because, for example, assume your reservoir is bosonic or fermionic. You have gapless excitations of the reservoir itself.
Right, of the reservoir itself, but for the system, I mean, right. So there's several things. So people have been looking at this lately. Dzerzhinsky has been one of the people looking at this whole master equation describing the infinite bath and the system and taking the whole evolution of that seriously. In Davy's approach, you trace out the heat bath, so the evolution is just living on this finite dimensional space, and there you do have a gap, right? There's this Gibbs state for the original Hamiltonian is the unique invariant state, and you're in a finite dimensional setting, and so there is a gap. And so if you ignore the heat bath, then this decays exponentially fast. Right. So this extended master equation approach this is another very interesting thing, right? And some of the latest papers of Dzerzhinsky, and I'm sorry I forget the name of his co-author, which is terrible, but they've written very interesting papers on this approach, and then that issue comes up, right? Because then in the infinite bath you don't have a gap.
Great, thank you.
Are there other comments? Elliot, do you have any?
Sorry, it's a beautiful talk.
Yeah.
And the density is amazing. Of the talk, I mean, the facts.
Yes.
The theorems.
Well, I hope it wasn't too dense, but it's
No.
it's hard to leave stuff out of this story. It's a story with many pieces, and if you leave some out, it gets tricky.
So for people who are here in Cambridge, we'll have a second talk at 4:30 this afternoon in person.
Oh, they're lucky. Very good.
Are there any other comments? Well, I'd like to thank Eric again.
Thank you,
Absolutely beautiful
Arthur.
talk.
Thanks.
Yeah.
Okay, thank you, everybody.
See you next week. Bye-bye.
Bye.
Bye.